Hello viewers, welcome to my channel Maths with VTC. In this video class, we are going to deal with the Euclid's division lemma. What is Euclid's division lemma? For any two given positive integers a and b, we can always find two integers q and r such that a is equal to bq plus r, where r satisfies the inequality, that is 0 less than or equal to r less than b. The integer q is called the quotient and the integer r is called the remainder. Remember, these two numbers are unique. For a given a and b, you can uniquely find q and r so that a is equal to bq plus r. Now let us see an illustration. I have taken two integers 42 and 5. So I have to find q and r. So when 42 is divided by 5, I get 8 times 5 is equal to 40. So when 40 is subtracted from 42, I get 2. Remainder. So what is quotient here? 8 is the quotient. What is the divisor? 5 is the divisor. What is remainder? 2 is the remainder. Therefore, I can write 42 uniquely as 5 into 8 plus 2. So this way, you can find q and r for any two given positive integers. What is Euclid's division algorithm? Euclid's division algorithm is the process of applying Euclid's division lemma in succession several times to obtain the highest common factor of any two numbers. So that is one advantage of Euclid's division algorithm. Earlier, we found HCF using prime factorization, but here another method which is comparatively simple. Here one problem. Use Euclid's division algorithm to find the highest common factor of 135 and 225. Now, we have to apply repeatedly Euclid's lemma for these two integers, 135 and 225. Naturally, 225 is the biggest number. 135 is less than 225. So, we apply division lemma to these two numbers in this way. When you divide 225 by 135, it is only one time. So the remainder is 90. Now, the remainder 90 becomes a divisor and the divisor 135 becomes the dividend. So when 135 is divided by 90, again you get 45 as the remainder. Therefore, 45 becomes a divisor, 90 becomes a dividend. When you divide 90 by 45, 2 times 45 is equal to 90. Therefore, the remainder is 0. Now the process stops because the remainder is 0. At this stage, what is the divisor? It is 45. So we conclude that the highest common factor of 135 and 225 is 45. So where you have to stop when the remainder becomes 0, you have to stop the process and the divisor at that juncture is called the highest common factor. Let us see the second problem. 196 and 38,220. So naturally 38,220 is the biggest number. Therefore, we divide it by 196. 195 times 196 is equal to 38,220. By this division, you can verify it. So straight away, you get 0 as the remainder. Therefore, immediately the process stops and the divisor at this juncture is 196. Therefore, the highest common factor of 196 and 38,220 is 196. So this is the benefit of Euclid's division algorithm. If you do prime factorization, it will be comparatively difficult. But this is a simple way. Let us consider the third problem. 867 and 225. So we apply division lemma to these two numbers. We divide 865 by 255. 3 times 255 is 765. When is subtracted from the number 867, we get 102 as the remainder. So 102 becomes divisor and 255 becomes dividend in the. Now 2 times 102 is equal to 204. So when it is subtracted from 255, 51 is the remainder. So in the next stage, the remainder 51 becomes the divisor. The divisor 102 becomes the dividend. So when you divide 102 by 51, 2 times 51 is equal to 102 and the remainder becomes 0. Now we have to stop. So what is the highest common factor? Because the remainder is 0. The remainder is 0 when the divisor is 51. Therefore, the highest common factor is 51. Let us consider this problem. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. So let a be any positive integer and b is equal to 6. So for a and 6 I am going to apply Euclid's lemma. So I can write a is equal to 6q plus r for some integer q and r such that 0 less than or equal to r less than 6. So these are the possible values of R. R can assume either 0 or 1 or 2 or 3 or 4 or 5. Therefore, I can write A like this. A is equal to 6Q or 6Q plus 1 or 6Q plus 2 or 6Q plus 3 or 6Q plus 4 or 6Q plus 5. Now you recollect the definition of even integers and odd integers. Even integers are of the form 2m, while odd integers are of the form 2m plus 1 for some integer m. Now you look at the forms of a. These three forms 6q, 6q plus 2, 6q plus 4. Clearly these are even integers because these are all multiples of 2. Therefore, we don't consider this. We are bothering about only the odd integers. Let us consider the remaining forms. 6q plus 1. This can be written as 2 times 3q plus 1. If you take 3q as k1, it becomes 2k1 plus 1, where k1 is some integer. Therefore, clearly 6q plus 1 is an odd number. Now consider 6q plus 3. This can be written as 2 times 3q plus 2 plus 1. In the first two terms, 2 is common. So you take it outside. What remains? 3q plus 1. You take that as k2. Therefore, this number becomes 2k2 plus 1, where k2 is a positive integer. Now you consider the last form, 6q plus 5. This can be written as 2 times 3q plus 4 plus 1. In the first two terms, 2 is common. Take 2 outside. What remains? 3q plus 2. If you take 3q plus 2 as k3, this number will be of the form 2k3 plus 1, where k3 is a positive integer. Hence, 6q plus 1, 6q plus 3, 6q plus 5 are of the form 2k plus 1, where k is an integer. Therefore, all these numbers are odd numbers. So, if a is an odd number, definitely these are all its forms. Hence, the problem is solved. Now look at this problem number 3. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? To visualize this program, I give you a diagram. First 32 members are present. Second 616 members are present. Now we do not know the number of columns, but clearly the number of columns must divide 32 as well as 616. Therefore, we have to find the highest common factor of these two numbers. For that, we apply Euclid's division lemma. So when we apply Euclid's division lemma, 616 when divided by 32, we get 19 as the quotient and 8 as the remainder. In the second stage, we divide 32 by 8. The quotient is 4 and the remainder is 0. Therefore, we have to stop here. The divisor is 8 at this stage. Therefore, the highest common factor of these two numbers is 8. Therefore, they can march in 8 columns each. That is the answer. Now you look at the fourth problem. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Okay, what it says, the square of any positive integer. So let us take a is such an integer, a be any positive integer and b equal to 3. Now for these two numbers, we apply Euclid's lemma. So we can find q and r such that a is equal to 3q plus r for some integer q greater than or equal to 0 and r is equal to 0 or 1 or 2 because r lies between 0 and 3 but r can assume the value 0 also. Therefore, a is equal to either 3q or 3q plus 1 or 3q plus 2. I have written all the possible values of the remainder r. Now, you square all the terms. So, a square is equal to 3q whole square or 3q plus 1 whole square or 3q plus 2 whole square. So, this is the square of the number. Now, when 3q square is expanded, it is 9q square. 3q plus 1 whole square is expanded, it is 9q square plus 6q plus 1. You remember the formula, a plus b whole square is equal to a square plus 2ab plus b square. I am using that formula. Or 3q plus 2 the whole square is equal to 9q square plus 12q plus 4, which can be written as 9q square plus 12q plus 3 plus 1. You look at the problem. We have to show that it is of the form either 3m or 3m plus 1. So accordingly, I have rearranged the terms. Now, you take 3 outside. In each form, you take 3 outside. Therefore, 9q square becomes 3 into 3q square or 9q square plus 6q plus 1. It is of the form 3 into 3q square plus 2q plus 1 or 3 into 9q square plus 12q plus 1 plus 1. So, these are the possible forms of a square. Now, if you take 3q square as k1, a square is equal to 3k1. Next, if you take 3q square plus 2q as k2, it is 3k2 plus 1. If you take 9q square plus 12q plus 1 as k3, some integer, it is 3k3 plus 1. Therefore, a square can be either 3m or 3m plus 1 for some integer m. Now consider the problem number 5. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8 for some integer m. Let a be any positive integer and b equal to 3. Why I have considered b as 3? Because when you find the cube of 3, you will get 9 as the factor. Therefore, I have taken b as 3. So when I apply Euclid's lemma for a and 3, I get a is equal to 3q plus r for some integer q greater than or equal to 0 and r is equal to either 0 or 1 or 2 because r lies between 0 and 3. But r can assume the value 0 also. Therefore, a is equal to either 3q or 3q plus 1 or 3q plus 2. Now you raise the power all the sides by 3. So a cube is equal to 3q whole cube or 3q plus 1 whole cube or 3q plus 2 whole cube. Now you recollect the formula a plus b whole cube. It is equal to a cube plus 3a square b plus 3ab square plus b cube. I invoke that formula. So a cube is equal to either 27q cube or 27q cube plus 27q square plus 9q plus 1 or 27q cube plus 54q square plus 36q plus 8. Just I have applied the formula a plus b whole cube. Now I am going to rearrange the terms in order to get the answer. So 27q cube can be written as 9 into 3q cube. Consider the second term. 27q cube plus 27q square plus 9q plus 1 can be written like this. In the first three terms, 9 is common, you take it outside. Therefore, 3q cube plus 3q square plus q plus 1. Look at the last form. In the first three terms, again 9 is common. You take it outside. So you get a 9 into 3q square, 3q cube plus 6q square plus 4q plus 8. So if you take k1, k2, k3 as the terms which are in brackets, you will get a cube is equal to either 9k1 or 9k2 plus 1 or 9k3 plus 8. Therefore, if a is any positive integer, then its cube will be of the form either 9m or 9m plus 1 or 9m plus 8. So that is the solution for this problem. Okay. Now let us discuss about irrational numbers. You recollect the definition of irrational numbers. A number S is said to be irrational if it cannot be written in the form of P by Q, where P and Q are integers and Q not equal to 0. Some examples of irrational numbers: root 2, root 3, root 5. These are all irrational numbers. Within radical sign, if a prime number is present, then definitely it is an irrational number. Pi, that is also an irrational number. Next, you see this fraction 0.10, 110, 1110, 11110, and so on. It goes up to infinity. Therefore, it is non-terminating and non-repeating. Therefore, this is also an irrational number. Now, let us consider an important theorem. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. Proof. You can refer the book for proof because it is beyond the scope of your examination. So we will verify this theorem with an example. Now 3 is a prime number. Obviously 3 divides 6 square. Therefore 3 divides 6. Hence you can understand the concept of the theorem. First, we prove root 2 is irrational. For this, we use the method of contradiction to prove this result. To prove root 2 is irrational, first we assume that root 2 is rational. Then we develop the concept. Finally, we will arrive at a contradiction. This contradiction is because of our wrong supposition. Therefore, we conclude that root 2 is irrational. That's our idea. So here also, we assume the contrary, that root 2 is rational. You remember the definition of a rational number. Then root 2 can be written in the form of r by s, where r and s are integers and s not equal to 0. Suppose r and s have a common factor other than 1. Then we divide by the common factor to get root 2 is equal to a by b, where a and b are co-prime. Co-prime means their common divisor is only 1. For example, if the fraction, that is r by s, is of the form 6 by 15, then you can reduce it by cancelling out 3, and which will be equal to 2 by 5. The reduced form is equal to a by b. That's all. For 2 and 5, the common divisor is 1. Therefore, 2 and 5 are co-prime numbers. Okay? Okay. Squaring on both sides and rearranging, we get 2b square is equal to a square. When you square root 2 is equal to a by b, you get 2 is equal to a square by b square. When you rearrange, you will get 2b square is equal to a square. Therefore, 2 divides a square. By the previous theorem, It follows that 2 divides a because 2 is a prime number and it divides a square. Therefore, 2 divides a also. Therefore, a can be written in the form of 2c for some integer c because a is an even number. Even numbers general form is 2k for some k. Substituting this value of a in the relation 2b square is equal to a square, we get 2b square is equal to 4c square, or b square is equal to 2c square. This indicates that 2 divides b square. Since 2 is a prime number, 2 also divides b by the same previous theorem. Therefore, b is also an even number and 2 divides b. Hence, a and b have at least 2 as a common factor. But this contradicts the fact that A and B have no common factors. They are co-prime numbers. Therefore, common divisor is only one. But we have 2 as a common divisor. This contradiction arrived because of our wrong supposition. Therefore, root 2 is irrational. Saying root 2 is rational is incorrect. So, this is the proof of the problem. Next, we are going to prove root 3 is irrational. In the same way, we are going to prove this result. Similarly, let us assume that root 3 is rational. Again, we take r and s to integers such that s not equal to 0 and root 3 is equal to r by s. In case r and s have a common factor other than 1, we divide by the common factor and reduce it to form a by b. Therefore, root 3 is equal to a by b, where a and b are co-prime numbers, or a and b have only one as the common divisor. Now, in the same manner, squaring on both sides, we get 3 is equal to a square by b square, or 3b square is equal to a square. Therefore, 3 divides a square. Why? Because of the same theorem, 3 is a prime number and it divides a square. Therefore, 3 divides a. Therefore, a is equal to 3c for some integer c. Because a is multiple of 3, therefore a is equal to 3c for some integer c. Substituting this value in 3b square is equal to a square, we get 3b square is equal to 9c square, or b square is equal to 3c square. This indicates that 3 divides b square. Again, applying the same logic, 3 divides b. Because 3 is a prime number and b because 3 is a prime number and it divides b square, 3 must divide b also. Hence, a and b have at least 3 as one common factor. Maybe other factors, but we can ensure that a and b have at least 3 as its common factor. But this contradicts to the fact that a and b are co-prime. They don't have any common divisor. Hence, our supposition is wrong. That is, root 3 is rational, is our supposition that is wrong. So, we conclude that root 3 is irrational. In the same way, you can prove that root 5 is irrational. Same logic. You assume root 5 is rational. You take r and s such that s not equal to 0, so that root 5 is equal to r by s. If it is if there is any common factor, you cut it out and reduce it to a by b. Therefore, root 5 is equal to a by b. Again, square both sides and rearrange the terms to get 5b square is equal to a square. This means 5 divides a square. 5 being a prime number, 5 must divide a also. Therefore, a is equal to 5c for some integer c. Substituting this value in 5b square is equal to a square, we get 5b square is equal to 25c square. Cutting out 5 both sides, we get b square is equal to 5c square. Again, applying the same logic, we get 5 divides b. Therefore, 5 divides A as well as 5 divides B. This means 5 is a common factor of A and B, which is a contradiction to the fact that A and B are co-prime. This is because of our wrong supposition. Therefore, root 5 is rational is wrong. We conclude that root 5 is irrational. So, same idea we apply for root 5 also. Now exercise 1.2, problem number 2. Prove that 3 plus 2 root 5 is irrational. You remember we have already proved that root 5 is irrational. Using that fact, we are going to prove 3 plus 2 root 5 is irrational. Let us assume that 3 plus root 5 is rational. Again, we can find co-prime integers a and b so that b not equal to 0 such that 3 plus 2 root 5 equal to a by b. Directly we can take co-prime numbers in the form a by b so that 3 plus 2 root 5 is equal to a by b. Therefore, 2 root 5 is equal to a by b minus 3 which is equal to a minus 3b divided by b. Or root 5 is equal to a minus 3b divided by 2b. Since a and b are integers and b not equal to 0, we get a minus 3b divided by 2b is rational because it is of the form p by q, q not equal to 0. Therefore, root 5 is rational, which is a contradiction because already we have proved root 5 is irrational. Therefore, 3 plus 2 root 5 must be irrational. This is our proof. Next, to prove the following are rationals. 1 by root 2, 7 root 5, 6 plus root 2. For all the problems, the underlying logic is same. We have already proved root 2 is irrational, root 5 is irrational. We are going to invoke that result. The way we give proof is the same method. We assume that the given number is rational and we are going to arrive at a contradiction. That is our idea. Let us look at the first problem. So we assume that 1 by root 2 is rational. So we can find two co-prime integers a and b, b not equal to 0 such that 1 by root 2 is equal to a by b. Inverting both sides, we get root 2 by 1 is equal to b by a, or root 2 is equal to b by a. Since a and b are integers, we get b by a is rational because here a is also not equal to 0. Because if a is equal to 0, we will get 1 by root 2 is equal to 0. Therefore, a is not equal to 0. So, b by a is a rational number. This means root 2 is a rational number, which is a contradiction to the fact that root 2 is irrational. Therefore, we conclude that 1 by root 2 is irrational. The same logic we are going to apply for the second problem, 7 root 5. Assume 7 root 5 is rational. Take two co-prime integers a and b, b not equal to 0 such that 7 root 5 is equal to a by b. Rearranging the factors, we get root 5 is equal to b by 7a. Since a and b are integers, we get a divided by 7b is rational. But this contradicts the fact that root 5 is irrational. Hence, we conclude that 7 root 5 is irrational. Third sum, 6 plus root 2. Again, the same logic. We assume 6 plus root 2 is rational. A and b are co-prime integers, b not equal to 0 such that 6 plus root 2 is equal to a by b. Rearranging the terms, we get root 2 is equal to a minus 6b divided by b, which indicates that root 2 is a rational number. But already we have proved that root 2 is irrational. Therefore, it contradicts to the fact root 2 is irrational. Hence, we conclude that 6 plus root 2 is irrational.